It's showtime. We have seen now how limits arise when we want to look at velocities or tangent lines, and we're going to go and develop some formal ways of notating and calculating limits. Today we're going to focus on limits in general and look at some numerical ways and graphical ways to compute them. We won't be looking specifically at velocities and tangent lines, though. We're just going to be looking at general limits of functions. And so let's look at an example. Now, in this first example, we're going to consider the function f of x equals x minus 1 over x squared minus 1 for values of x near 1. And instead of going through and doing a whole bunch of calculations, I'm just going to give you some tables of values so we can look at them and not worry about doing all the calculations this time. So first, we have a table of values, and in each of those, x is greater than 1. We said we wanted values of x near 1, and we're going to do this in two halves. We're going to look at some values of x that are greater than 1 as we get closer and closer to 1. And we're also going to look at some values that are less than 1 because we want to look at both sides, because occasionally we might have different behaviors as we look at the two different sides. But I'm getting ahead of myself. Let's look at these values. If x is 1.5, f of x is 0.4. And then if we start to look at 1.1, 1.01, 1.001, 1.0001, numbers that are getting closer and closer to 1 itself, the values of our function are getting larger, but they're always less than 0.5. We're getting numbers that are growing, 0.476190, 0.497512, etc. I don't want to say all of these numbers and have some poor person transcribing them somewhere on the internet. Thank you, whoever is transcribing this video and all of them. But the basic point is that these numbers happen to be growing, and we can see that they're getting closer and closer to 0.5. Now, these are values of x that are greater than 1. Let's look at some that are less than 1 and see what's happening on the other side. So here is another table of values. And in this case, we're looking at values where x is less than 1. But for each of these values, it's getting closer and closer to 1. Now, in this case, if we look at the function value, we start with 2/3 when x is 0.5, and then as we get closer and closer to x equaling 1, the function values in this case are getting smaller and smaller, and it looks like they're getting closer and closer to 0.5, similarly to how the other function values were getting closer and closer to 0.5. Now, these are larger than 0.5 and these are smaller, but that's totally fine. In both instances, on both sides, we are getting closer and closer to 0.5. And so that means that the limit in this case is 0.5. And there are ways to write that, and there are ways to say that. The way that we would write this is by saying the limit as x approaches 1, because that's what's happening, x is getting closer and closer to 1, the limit of x minus 1 over x squared minus 1 as x approaches 1 is equal to 0.5. So we write LIM as an abbreviation for limit. Below the limit, we write what the variable is approaching. In this case, x is approaching 1. It's getting closer and closer to 1. And then on the right-hand side, we put the function that we're looking at, which in this case is x minus 1 over x squared minus 1. And we say the limit as x approaches 1 of x minus 1 over x squared minus 1 is equal to 0.5. Because this is a named function, it is f of x, we could also say in this case the limit as x approaches 1 of f of x is equal to 0.5, right? Because this function was called f of x, and it's equal to x minus 1 over x squared minus 1. Either way we can write it, but this is how we write it, and that's how we say it. The limit as x approaches 1 of f of x is equal to 0.5. Now, we can clearly see that as x is approaching 1 from the right-hand side, from numbers that are larger than 1, and from the left-hand side, in both instances, the function values are getting closer to 0.5. And intuitively, we can see that this is a limit, but it's not quite enough that the values are just getting closer to 0.5. There's one more thing that we need to be true for that limit to actually be 0.5. And this is the thing that we need. We need to be able to make the values of our function f of x as close as we like to 0.5 by taking x sufficiently close to 1. This is a concept that students really struggle with the first time they learn about limits. And I expect that you don't even understand what that sentence means, which is totally fine. Let me try and explain what I mean by this. If we look at this table of values here, we can see that as we pick values of x that are closer and closer to 1, the values of f of x are getting smaller and smaller, and they're getting closer and closer to 0.5. Now, if we were to continue with this table of values, and we were to pick, for example, 0.99999, if we were to add an extra 9 to the end of that, what's going to happen is we're going to have an extra 0 in the middle, 0.5000025. And what's going to happen is the function value is going to get even closer to 0.5. Now, what I mean by we can make the values of the function as close as we like to 0.5, what that means is that for this limit to equal 0.5, we need to avoid the situation where if we keep adding 9s and we keep getting closer and closer to 1 for our x, the function eventually stops getting closer to 0.5. And let me try to show you kind of graphically what I mean here. Let's pretend that this whole limit thing, let's use a metaphor here. Let's pretend that it's a race. And the end of the race, the finish line, is at 0.5. And what happens is, as our x values get closer and closer to 1, our racer is getting closer and closer to 0.5, right? At some point, it's at 0.502. At some point, it's at 0.5002. It's getting closer and closer. I mean, these numbers are bigger than 0.5, but I think you know what I mean. It's getting in closer and closer. What we need to be true is that we can keep picking values of x that are closer to 1, and our function values continue to get closer and closer to 0.5. If there happens to be a barrier somewhere such that no matter how many 9s we put in here, we never actually get past that barrier and closer to 0.5 than that barrier, then the limit isn't 0.5. The limit is something that comes slightly before that. So what we need here is that not only are we getting closer to 0.5, but there's not a barrier before that where we stop getting closer and we don't get past that barrier. So now that we've discussed that, we can give a bit of a definition for what a limit actually means mathematically. So here we go. Suppose f of x is defined when x is near the number a, but not necessarily a itself. Like this function was defined near 1, but it was undefined at 1. So it doesn't have to be defined at the number that x is approaching. Then we write this and say the limit of f of x as x approaches a equals L. If we can make the values of f of x arbitrarily close to L, which means as close to L as we like, by taking x to be sufficiently close to a on either side of a, but not equal to a. What this is saying is the reason this limit is equal to 0.5 is because on both sides, we can pick values of x that get close enough to 1 such that f of x is getting closer and closer to 0.5. And it never stops short behind a barrier before 0.5. It's always getting closer and closer in to 0.5. I want to strongly encourage you to go through some of the example problems because it is really good to get practice looking at these tables of values and really getting a sense of how the values are getting closer and closer to the limit.